So thank you very much, David, and welcome everyone to the homotopy harnessing higher structures program, but specifically for the workshop on equivariant and motivic homotopy theory. I don't really have anything more to say than I'm looking forward to talking to all of you over the week, and it's my job to introduce Dan Duggar to talk about involutions on surfaces. Dan.
All right, well, I would like to... Darn it.
Is that good? Yes? Yeah. I hate these things, but we'll deal with it. We'll just end the pocket. Okay? Is this okay? Yes? All right. Yeah, so I'd like to thank the organizers for inviting me, and especially for the little extra poking that is needed to somehow get me to go anywhere. But I appreciate it. So I'm talking about a very basic problem that I got interested in a few years ago. I would like to claim this is the most basic problem that we will hear about this week. But here it is. So when I talk about a surface, I mean a closed two-manifold today. And I realized I forgot to actually see beforehand how visible my writing is from the back of the room. So you think it's okay, huh? I've learned not to trust anybody, so I always walk back and look. But okay, so we all learn about these in our very introductory 600 algebra courses, 600 whatever it is, introductory topology courses. So what are they? So we have the TG, and we have N sub R. And that's all of them. It's a complete story there. Sometimes today, I'm going to have to unify these two cases. And I'll use beta to denote the dimension over Z mod 2 of H1. So it's R here and 2G here, and I'll just call this the genus or the beta genus. So we know what they all are. We know they're homology groups or cohomology groups with Z or Z2 coefficients, so the interesting cases there. And not only can we do the computation, but we have a sense of what the geometric story is. So for example, if I draw this picture, then I know the cohomology groups are Z, Z4, and Z. And I know to draw these cycles whose fundamental classes represent those four elements, right? And that cycle has a fundamental class representing that. Okay. So that's your brief review of introductory topology. So the question is, what's the Z2 version of this? So understand the analogous theory. For Z2 surfaces. Okay, surfaces with an involution on them. Now, when I first started thinking about this, I was convinced everybody knows how to do this. This has got to be something completely classical and very easy to understand. Oh, and I should say, what do I mean by this? So I mean, first of all, write down all the possible surfaces with involution on them, up to isomorphism. And for this, I want to use the Bredon cohomology. And either constant coefficients with Z or constant coefficients Z2. So I think in the case of surfaces, it doesn't really matter. But for all intents and purposes, smooth, linear, whatever niceness you want. But I think for surfaces, they're really all the same. Okay. As soon as you get up to 3 dimensions, it's all different. Okay. Okay, so as I was saying, I thought this would be a very easy problem. I asked some people about it, and they said, oh yeah, just go do this and this and this. And it somehow was never quite working, and I just felt really stupid. And eventually it somehow all got figured out. And it's not hard, but it's also, there's some sort of non-trivial aspects to it that I want to explain. Okay. So where do we start today? Just some notation, I guess. So I want to start describing these spaces with Z2 actions, and I use motivic notation. So SPQ is a sphere, P is the topological dimension, and Q is the weight. And so P minus Q is the dimension of the fixed set. The ones we'll need today, so here's S11. Here's S21. It's that reflecting sphere. Oh, I should say S10 is the trivial action. Similarly for S20. S22 is the rotating sphere. So you have a north and south pole and an axis. And I'm somehow being lazy today, but I find it useful to mark the fixed set in color. Like so. I'll add to this as we go along. But so what are some basic things where you can do to these gadgets? If you have an X, and you have a point here, which is conjugate to a point here. So sigma will always be the involution. Okay. I want to use sort of surgery operations on this. So one thing you can do is you can cut out a little neighborhood here and a neighborhood here, and then you can attach stuff. Okay. So what are some options? I could add something here and add the same thing here and have them be conjugate. Right. So dt is going to stand for dual tori, and it's just taking a connection with a torus here and a torus here. Another thing you can do is you can add an RP2 and an RP2. So the acronym I've been using for that is DCC. It stands for dual cross caps. Put a cross cap there and a cross cap there, and those are your RP2s. Another thing you can do is you can take a certain tube where the Z2 action flips the two ends, and you can glue it in there and there. Okay. Let me draw some tubes over here. So here is S10 cross R11. So the S10 is fixed. The R11 is the sign action. These tubes where the two ends are fixed, whereas R11 I've been calling antitubes, just to distinguish them from the different case where you have R10 and the ends are fixed. So this is an S10 antitube. You can do an S11 antitube. It's the same idea. Fixed set is here and here. So those are the only two kinds of tubes I'm going to have to use today. And then there's one last operation that I'm going to need. So here's a Mobius band. There's going to be a fixed circle inside of it. And each of these fibers is an R11. So that's conjugate to that, x and sigma x, all the way along. Okay. The boundary of this thing is a circle without any fixed points. So it's the antipodal circle. And I probably should have added that to our basic picture up here at the very beginning. So the spheres I drew were the representation spheres, but you also have the antipodal circle, the antipodal 2 sphere. And so one thing you can do with this guy is, if you have an x with a fixed point, an isolated fixed point. Here, let's put it in color. So when I cut out a little neighborhood, I have an S1 antipodal action around that boundary. And so I can cut that out and get rid of the fixed point and glue on this Mobius band. Okay. I've been calling that operation FM. Okay, so you're changing a fixed point to a Mobius band. These acronyms are horrible and silly, but they seem to be okay for me. There are other kinds of surgery operations you can think of for surfaces with involutions. These ones seem to be the ones that are actually useful and sort of for my problem. Okay, so what do I need to say next? Okay, so let's talk about the easy case. So Z2 action is on the tori. Okay. This case really is completely classical. So I think this was done by Felix Klein in the 1890s. So at the very, very beginnings of topology, this problem was already solved. So what do you have? So you have the free actions. And there are not too many of those. So you have always the antipodal action on the torus. So that's something, just put it in 3 space in the usual way, and pretend that's the origin at the center, and x is conjugate to sigma of x on the bottom side. Right. In the case of odd genus, you could put an axis through the center and rotate. So in the case of 2u plus 1, you have the rotation action. Okay, and these are the only free actions on tori. Easy prove this by covering space theory. What about the non-free actions? So you have things that look like this. And you put a spit through the center and rotate. What is that? Using sort of this crazy nomenclature. So over here, I have an S22 that I started with. I added dual tori, but then I did it twice. So there's 2 dual tori operations. And then I added an S11 antitube to get here, and then I added one more to get there. Okay, so that's that space. What else do you have? You have a very similar thing. And I'll draw a smaller example, where you put a plane in the middle. So you reflect. So you have these three fixed circles. So what did I start with? I had a S21, that's my reflecting sphere. I added dual tori, and then I added 1, 2 antitubes. And this time they were S10 antitubes. There's that guy. Okay. And then there's one more class. I'm going to put it over here. These ones you can draw nice pictures for. This one is a little harder. So these look like T, G minus C anti plus C S10 antitubes. So what is this? So take some antipodal torus. There's X and here's sigma X down at the bottom. Cut a hole. And then put in your S10 antitube, and then do that as many times as you want. Okay. How do I know that this one's not secretly one of these? Well, it's clearly not any of these, but it might be this one. Right? You have fixed circles here. You have fixed circles here. Here, maybe I'll put in some more. Here's another fixed circle on my picture. Well, here's the difference. If I remove my fixed set here, I've disconnected the space. If I remove my fixed set here, I have not disconnected the space. Okay. So this picture is called, or this action is called separating. This one's non-separating. Okay, and that's the whole story. No, you're right. Thank you. Just saying if you're awake. All right, if you count all this up, it's not hard. There's not too many of these. There's 4 plus 2G actions total. I think I forgot to write down the trivial action. That's one of these 4 plus 2G. Okay. All right, this is kind of the answer you would expect. There are not too many of them. You can make a list. It's not too hard to tell people in 5 minutes what all the actions on a torus are. So what about on the non-orientable surfaces? Yeah.
So is it clear that it does not depend, this kind of gluing in, so the dual torus or something like this does not depend on the embedding of the disks?
That's right. It does not depend on the embedding of the disk. Yes, for the same reason as classically. Yeah. Okay, so what about on the non-orientable cases? So this, I'm convinced, was not known classically. So there was some work done in the 1920s by Scherer, and he figured out a bunch of them. And then there's this huge gap in the literature where nobody actually thought about them at all. And in the 1980s, people came back to this, and the Fuchsian group people sort of spent some time thinking about this, but I can't find any kind of thing close to complete classification in their papers, although they got further than Scherer had. But I think I know the answer now, and so here's the theorem. So the number of actions on NR is the following. I have to look it up. So there are several cases depending on the parity of R mod 4. So in the case where R is 0 mod 4, It's 1 over 64 r cubed plus 18 r squared plus 152 r. Of course, you expected that answer. When r is 3 mod 4, it's 164 r plus 1, r plus 3, r plus 5. And the other two I'm going to be too lazy to write down, but they're very similar formulas that all start out looking like r cubed over 64 plus some junk. Okay. Okay, so this is the first surprise, which is that there are way more of them than you would expect, right? And it's hard for me actually to write you down a whole list and say, okay, here's how you do it because the number is so big. Okay. There is an algorithm. It's not very hard, and I'll sort of give you a clue about that algorithm. Now let's do an example. Okay, so I think I need my cheat sheet again for this example. So on N2, which is the Klein bottle, you have 6. So you have the trivial action, which I'll mostly stop listing. That's always there. The others are S22 plus 2FM. Here, let's just quickly draw a picture of that one. I'll sneak it on the board over here. So here's S22. That's our rotating sphere. And what I do is I cut out neighborhoods of those 2 fixed points, and I sew in that weird Mobius band from over there. So this becomes a Mobius band, this becomes a Mobius band. So that's the connect sum of 2 RP2s. That's my Klein bottle, and it's rotating. Okay, what are the other ones? S22 plus S10 antitube. There's a reason I'm bothering to write all these down. S21 plus DCC. S2A plus DCC. And S2A plus and 1 antitube. 1, 2, 3, 4, 5, 6. Okay, that's all of them. Okay, so how do I know that that's all of them, and how do I tell them apart? Well, let's first answer the second question first. So what are the obvious invariants you can write down? So there's F, which is the number of isolated fixed points. You can also look at fixed circles. And the fixed circles come in 2 types. So a circle inside a 2 manifold has a normal bundle, which is either trivial or not trivial. It's either trivial or the Mobius band. So you have the 2-sided circles and the 1-sided circles. So these are 2-sided fixed circles. Sorry about the blackboard technique. C minus are 1-sided fixed circles. Another invariant that's easy to sort of rip off is Q. Q is always plus or minus. And this is whether or not the quotient space is orientable. So Q stands for quotient here. So this is orientability of the quotient. Okay, so let's just read off these invariants real quickly. So I had 2 fixed points, but then I got rid of them and I changed them into Mobius bands. that gave me 2 of these untwisted circles. The quotient is the same as the quotient here. It's positive. Here I have 2 fixed points. I have my fixed circle, which has it's 2-sided. I don't have any of these. Still positive.
You have 2 fixed circles or fixed points.
Here? I don't think so. So that's this picture. I had 2 fixed points, but then I cut them away, right? So I excised those neighborhoods, the fixed points are gone, and I stored in my Möbius bands.
Could I ask a naive question? Why?
Sure.
So orientability is like a manifold thing. Why is the quotient a manifold?
It's a manifold with boundary, right? So if you think about, so the places where it's not a manifold are on the fixed set, right? The fixed set is either a point. So if you have a point with 180-degree rotation, right, then what you don't have is a manifold anymore, but it's the cone point. It's just this, right? So it's still a topological manifold,
Yeah.
right? If you have a fixed circle, then you're looking like this, and you just have that boundary. I mean, yeah.
I see. So, okay.
Yeah.
Got it.
Okay.
This works out. It just works out.
It just works out. Yeah, exactly. Okay, so what do we have here? We have 1, nothing, nothing, minus. Let me just refer to my cheat sheet so I don't have to think. Of course, my cheat sheet is wrong, but so next one 0, 0, 0 minus 2, 0, 0 minus. Okay, great. So one thing you learn in this particular example is that these 4 invariants completely distinguish all the actions, right? Somebody gives you some random action on the Klein bottle. All you have to do is compute those 4 invariants. You look at your chart and you figure out which one it is, okay? That's the nice thing that could happen. But I'll get to it in a minute and explain why it's always not so nice, or not always so nice. But this is your first guess, that you're going to try to classify actions by classifying these tables, right? What can these different invariants look like? And the theorem from Scherer, the 20s. So f plus 2c is always less than or equal to beta plus 2. And f is always congruent to c minus is congruent to beta mod 2. C, thank you. C is the total number of fixed circles, which is that. C plus plus C minus. In modern times, this is usually gotten from Smith theory. The easiest way to do it is the same way that Scherer basically did it, which is to prove that all those inequalities and equivalences are invariant under the different kind of surgeries you can do. So if somebody gives you some weird, horrible surface with involution, you latch onto some structure, either a fixed point or a pair of fixed points or a circle. You do some surgery to reduce the genus, and you keep doing that until you have something you understand. And because all of these are invariant under those surgeries, you just check these for the first few spheres, and then you're done, basically. Okay, so what does this mean? This means that in practice, you can make a list of all the possibilities for what you could get on this side, right? Beta constrains what f and c can be, so there are finite many examples for those. Not everything can occur. They're required to satisfy this congruence condition. So you make a big list of these things. Okay. It turns out not all of the things on your list are realizable. So there's a few that you have to figure out aren't. Counting the things on this list is roughly these numbers here. Okay, not exactly the numbers for reasons I'm about to explain, but roughly the numbers. Okay. So there's some weird number theoretic problem, right? to classify all tables that satisfy these inequality and this congruence. And it turns out to have a nice answer. It's basically this product here. For reasons I have no understanding of other than you do some awful induction, this nice answer comes out. But the number of possible sort of things on your table is fairly easy to count.
Good question.
Yes.
It looks like that fourth invariant is redundant in terms of distinguishing your actions. Am I right about that?
It's not. Unfortunately, in this case, it does look like that, but it's not in general. Yep. Okay. Right. So in fact, I'm not going to do this example in detail, but so on N6, you have 28 actions. 24 of them are classified by these invariants, classified uniquely. And actually, I have to add in one more invariant, epsilon. This is the separating versus non-separating invariant. I didn't need that for the Klein model, but in general, you do need that. Okay. So there are 4 left over that you can't distinguish using all of these. And the question is, what comes next? And this is essentially where the literature ends. So looking back to the 1980s in these papers by the Fuchsian group people, they sort of realized you can write down this table. They sort of got that far, but they did not understand how to deal with the last few cases here. And what turns out is that there was sort of a piece of algebraic topology that was missing from the story that I want to tell you about. And let me throw up one more example before getting to that piece. So here are some spaces with involution. Okay, you know what I mean by this now. You take the antipodal sphere, you add 2 pairs of dual cross caps, you add an S10 anti-2. Here I take the antipodal torus, I add 1 pair of dual cross caps and an S10 anti-2. And this third space I'm just going to make with the picture. So you take 2 pentagons, put that in color because we're going to be reflecting. You label them like this, D, B, C, A, B, D, A, C. And then in addition, I'm going to cut a hole in the middle of each and make an identification. So this is identified there. So basically, you reflect and take the antipodal point. So this, I reflect and take the antipodal point is identified there. Okay. These are 3 actions on N6. 2 of them are the same, 1 is different. So there's your problem if you're getting bored. Figure out which one's different. 2 are the same, which is not. Okay, for me, it's not at all obvious how to solve that problem, right? Oh. So So the thing that's missing from the story turned out to be really a piece of algebra. So what can you do here? So I have my surface. V is going to be H1, Z2 coefficients. And on this surface, I have the cup product. So the cup product takes me up into H2, which is just canonically Z mod 2. So we can think of this as a bilinear form. In fact, it's not degenerate and symmetric. In fact, we know even more about this. So we're really interested in the case right now where we're talking about these non-orientable guys. And so this up to a change of basis is always the sum of squares form. So I'll just call it Euclidean. Okay, so we know exactly what this form is. My involution on the surface gives me an involution on this vector space, which preserves the form. Okay. So I get an element sigma in the automorphism group of this form. That's V with the cup product. Okay. So that's just the automorphisms of the Euclidean form, so this is really just the orthogonal group. So what I mean by that is it's R by R matrices satisfying the usual condition A transpose equals the identity. Okay. So an involution on my non-orientable surface gives me one of these orthogonal matrices. It's not quite well defined. I mean, if I chose an isomorphic model of this surface, I would get a different matrix, but it would be the same up to conjugacy. Okay, so I get a well-defined conjugacy class here. So the algebraic problem is to classify conjugacy classes of involutions in the orthogonal group. And when I got to this point in this story, I thought, look, this is completely classical. Clearly, this has been solved somewhere. You just need to go to the MathSciNet database and look through everything and find the solution to this problem. And in fact, you find lots of papers that are, in fact, about classifying conjugacy classes of involutions in an orthogonal group. It's a different orthogonal group. So what happens is that the algebraists, they want to always be dealing with simple groups. So their orthogonal group are the symmetries of a quadratic form. Okay. That's fine. It's the same thing when the characteristic is different from 2. But in Z mod 2, their orthogonal group is not this orthogonal group. So it turned out, as far as I can tell, this is not in the literature. In the case when R is odd, you're OK. In that case, it's easy, because this Z mod 2 orthogonal group ends up being the symplectic group, dimension 1 less. Okay. The symplectic group is simple, and so you can find this treated in the literature. There's a paper by Oshbacher and Zeitz. And they tell you to do the following thing. Okay. So what are the obvious invariants you can sort of write down? So the first is just to take the rank of the lambda equals 1 eigenspace. So take the rank of sigma plus the identity. Okay. That's invariant under the general linear group action. So it's certainly invariant under the conjugation by orthogonal group. This is usually called something like the Dixon invariant, where the D comes from. The second thing you can do is you can write down a map from your vector space to F2 which sends a vector to sigma v cup v. Sorry, too many things that look like v's there. Okay, that looks quadratic, but because we're over F2, it's actually linear. So this is a linear map. It has a rank, and that's called the alpha invariant. This alpha invariant is always between 0 and 1, or 0 or 1. This rank invariant, the D invariant, is always between 0 and roughly R over 2. And Aschbacher and Zeit say that knowing these two numbers completely tells you the conjugate class of an involution. Okay, fine, you're solving. This is actually not the case we need, though. So when you're looking at actions on n sub r where r is odd, it turns out the table tells you everything. Okay? In those odd cases, the table already distinguished all the possible actions. You don't really need that story. It's the r even case, like this one, that you care about. So what happens when R is even? So this orthogonal group is not simple. It's the symplectic group, semi-direct product, some very strange representation. I won't tell you what that representation is, but you can figure this out.
Does that say R minus 1?
That says R minus 1. Okay? So if it was the symplectic group acting on R minus 2, he would think, okay, that's just easy, that's the standard representation. This is R minus 1. You can write this representation down. The formula is not hard, but it's weird. It's not really relevant for the rest of the talk. Okay, here ends up being the key. So here's a weird function from the orthogonal group to itself, what I call the mirror function. So you take the orthogonal matrix, and its mirror is what you get by flipping all zeros and ones. Okay, totally weird thing to do, right? This is not a homomorphism. It's sort of remarkable that it preserves orthogonal matrices, right? But you can check that it does. And it only does it in this case when R is even. Okay. The other miracle is that, in fact, it also preserves involutions. It's not hard to check, but it's surprising. So here's what you do. So I guess I'll write this as a theorem. So 2 parts. So given one of these involutions in my orthogonal group, I can look at the Dixon invariant, the alpha invariant, the Dixon invariant of its mirror, and the alpha invariant of its mirror. Okay. So just to remind you, I guess the Dixon invariants are integers, the alpha invariants are in Z mod 2. So. And this completely classifies conjugate classes of involutions. Okay. I'm not telling you the whole theorem, right? You can exactly write down what possible invariants occur. You can count how many. You can sort of solve everything you need to solve about these invariants. I've been calling this the double Dixon invariant because it's the sort of the Dixon invariant doubled. So that. Okay, and so that was the topological part. So the topological part is that Z2 actions on surfaces are completely classified by everything I told you so far and this last invariant. Okay? That distinguishes everything. So that's nice. So you've solved the problem. And in fact, I want to just point out, this is extremely computable, right? These D and the alpha invariances is just linear algebra. You write down a matrix, you compute a rank of it. The mirror is this easy operation where you flip all zeros to ones, right? It's a very easy thing to compute. If you want an exercise, take those 3 examples, compute their invariant. I think what you find is that these guys have DD invariant 3, 1, 3, 1. And this guy has 3, 1, 2, 1. Whoops, of course I reversed it. Something like that. In any case, this is exactly what's needed to distinguish that space from those. Okay. All right, how's my timing? I have 15 minutes. This is amazing. So I'm leaving out a lot. Like I did for the Klein model, right? There's an algorithm for exactly writing down all the possible actions. That algorithm is a little bit unpleasant. There's 4 or 5 cases you have to keep track of. It's not pleasant to write on the blackboard or even to read, although it's very easy to program into a computer. So you can count how many, that's how I got those weird numbers, etc. But let me now turn to cohomology. So I'm going to be dealing with this bi-graded theory. And let's just do Z2 coefficients. So the constant Z2 Mackey functor. So my cohomology of a point is usually called M2. And it's this ring. So there's P and there's Q. And it looks like this. Okay, everything here is a dot, but I'm going to be sloppy. And dots are Z2s. So this is 1. This is usually called tau rho, theta over tau, theta over rho, etc. Okay, so I have this weird ground ring. Here's some modules over this ring. So AN is this module. It's really the cohomology of an antipodal sphere. Like that. Okay, so my diagonal lines are multiplication by rows. My vertical lines are multiplication by taus. I guess I could give this a name. This is what? This is M2 with tau inverted, localized, or sorry, with rho n plus 1 killed. Okay. Now, these are not the only M2 modules. There's lots of M2 modules, but these are the only ones that show up in cohomology of finite complexes. So that's a very recent theorem of Plover-May's. So if X is a finite Z2 complex, then the cohomology is a direct sum of, well, shifted copies of these things. Okay, you get the idea. So for surfaces, what we care about is we care about M2, we care about A0, A1, and A2. That's all that's going to appear. So M2, A0, A1, and A2. Those are our complete building blocks for the cohomology of surfaces. So a student of mine, Christy Hazel, has computed the cohomology of all the surfaces, and I can tell you exactly what it is. I had actually hoped that she could be here to give this talk instead of me, but she wasn't able to make it. And I sort of won't write down the theorem because it's given lots of cases, but she's computed all the cohomologies. She's actually also done this integrally for all Z2 surfaces. And I just want to show you how two examples, how they work out. So I'm going to start with the non-trivial action in RP2, which we usually call RP2 twist for some reason. Okay. So start with the usual picture of RP2. So it's identification space on the disk. And I'll put a pen in the middle and rotate this 180 degrees about that point. So you have a fixed point there. And on the boundary, this point maps here, but that's really the same. Okay, so this is a fixed circle along the boundary. So let me label some obvious cycles here. So I'll call that guy Y. I'll call this guy X. The fundamental class of X is going to be an H11. The fundamental class of Y is going to be an H22. All right, you look at the normal bundle about your point. And locally about that, it looks like an R22. This is all fixed, so locally about X, it looks like an R21. So that was a mistake. There's D. D is a fixed circle, so that's a nice cycle, an equivariant cycle. That'll have a fundamental class. Again, looking at the normal bundle, that looks like an R11. It's there and here, so they're switched. So I have the fundamental class of D in H11. And let me add one more thing to the picture, which is this guy. We'll call him C. Right, there's another fixed circle. Sorry, not fixed by, the individual points are not fixed, but the circle itself is invariant under the Z2 action. This is a copy of S11. So I also have C in H11. So you immediately write down all of that stuff. Intersection theory in the transversal case works exactly the same as you're used to. So you can immediately write down the formula as C dot C is Y. Right, if you perturb C a little bit, there you go, it only intersects in Y. C dot D geometrically should be X, but the dimensions don't quite work out, right? This is C dot D, this should be an H22, X is an H21, so this is where you need the tau. These are all cohomology classes. Okay. So those are some obvious geometric relations. here's the cohomology. So the cohomology looks like, so you have the cohomology of a point. Up here in dimension 1, 1, you have another free thing. And over here in dimension 2, 1, you have another free thing. Okay. If I look at that purple dot, that's an H21, and X is an H21. There's no choice. That has to be X. Okay. If I look over here in H11, well, I have two things. I have a yellow dot and a red dot. The red dot is just rho times 1, but then I have that yellow dot. But you see, I have two things in H11, D and C.
Did you say the yellow? Where is the yellow thing located at that point? What's the class? What's the yellow?
There's lots of yellow on the board, so
I'm a little confused.
yeah. So ignore the colors.
Okay, that's X. Which one is? Oh, D is the yellow. Oh, I see. The yellow's on top. The colors on top are corresponding to the colors on bottom.
No, I lost track of the colors. So
what is the one that's yellow in the bottom?
That's exactly the question he's about.
Oh, I'm sorry. Okay, very good. I'll wait.
right. Okay. So right. So it's hard to point to this class and say what is it? Is it C or D? Right. In fact, it's not quite well defined. Like you could say, all right, this is going to be the unique class in reduced cohomology. But I can only talk about reduced cohomology if I choose a base point. And I might choose that base point, and I might choose that base point, and I get different answers. So what actually happens here is that the class of C is the class of D plus rho. You have that basic connection here. So you could choose to call that yellow dot C, in which case D is the yellow dot plus the red dot. Or you could choose to call that yellow dot D, in which case C is the other one. Is this the question you're asking, Mark?
I guess so. Yeah, I mean it is. Yeah. Okay.
This dimension.
Yeah. I'm good. Thank you.
Yeah, so C, D, and rho are all in dimension 1, 1.
I guess what I was confused by is isn't that gap between the 2 points like distance 2?
Between here and here?
No, between the cone and the dual cone.
Yes. So that's distance 2.
So those cones aren't really touching the x-axis. Right?
No, in fact, I mean, if you just, those cones are there, but they're not really part of the story I'm telling right now.
Okay, cool. I just want to make sure I know where
Yes.
these classes are living. Okay,
Yes.
that's good.
Yeah.
Thank you.
Yeah, one of the annoying things about talking about this subject is you really have to take the time and draw the whole grid. Otherwise, the picture somehow doesn't come out looking very good. Okay, I got a couple of minutes left. So what else can we say here? So what's y? So y was in H22. So that lives here where all that stuff is. Okay. There's that big overlap. So it's some combination of tau x and rho, let's call this guy, let's decide to call that guy C, and rho squared. And you can figure out what it is because it's C dot C from there. And if I dot C on both sides, that's C dot D plus rho C. And we've already said that C dot D is tau x. Okay. So the fundamental class of y is what? I guess it's the purple class plus the yellow class in this picture. Likewise, if you wanted to do, for example, D dot D. Well, D dot D is very hard to do geometrically, right? Because you can't move that fixed circle off of itself. Okay, so this is the case where you can't sort of easily do the geometry to get a simple intersection. But you can get it from this formula. So if I just dot D with everything, then that's C dot D plus rho D which is your tau x plus rho d. For those of you in the motivic world, like this is a very basic relation, the motivic cohomology of these, A1 minus 0 mod plus or minus 1 that came up in Blavatsky's work. Back in the day, I think we used to write A squared as rho A plus tau B. This is that relation. But you see somehow backtracking it into this more geometric world, what you sort of see is that really that relation is a very simple relation geometrically that's just been re-encoded using this change of basis. Okay. This is something that was not clear to me for, 20 years, I think? Anyway, I'm out of time, but what I sort of want to say here is that you can do these stories for every surface, okay? So in Z2 coefficients, you can find cycles, you can draw nice pictures, you can sort of label everything in your diagram in terms of fundamental classes. And it's sort of all very pretty and makes sense and is consistent, and it's nice. I like it. All right, thank you.
What about the squaring operations in that picture?
Yeah, so I happen to not know the answer to that. I mean, look, we could figure that out, not hard, but I don't know it off the top of my head. Yeah.
Which of the invariants can you read off from either the Z mod 2 or Z cohomology?
So I wish Christy were here because she has all this stuff in her head, and I don't. You can read a lot off, but I can't tell you exactly what the answer is, so this is all going to be in Christy's paper. I can say this that's relevant. So there was all kinds of intergravity conditions. This had to be this mod 2, or there's lots of those Scherer conditions. Just gave you constraints on this, right? And when you look in the cohomology of these surfaces, you find those constraints appearing in terms of how many of these, or how many of these, or how many of these, right? So you'll get some number, like the number of A0s is, F minus 2C minus over 2, or some weird number that you don't think is an integer, but it is an integer because of those constraints. Okay. So there is an answer to your question, I just don't happen to know it, but Christy does. Good. Yeah, Tyler?
Do these invariants you get from kind of mirroring this element sigma in the orthogonal group, are they kind of pure algebra, or do they have geometric or cohomological interpretation?
Right, so that's a great question, and I do not know the answer to that either. So I'll tell you the story why all my answers are I don't know, because somehow I thought this was going to be an easy problem, and I was going to solve it in like 3 months and be done with it and go on to the next step. And instead it took something like a ridiculous amount of time. And so by the end, I was like so tired of it. It was one of these things where it's like, okay, just get it out and get done with it. But there's like so many questions left over. The algorithm for like proving that this is the classification is a mess. Like somebody's got to clean that up. Knowing the geometry behind what this invariants are telling you, nobody's ever touched that. Like there's so many unanswered questions here. Kristen?
What's the relation with the Euler characteristic? That's an element of the Burnside ring. It's related to the growth and decay group of R. That's like a quadratic form. There are ways of interpreting the motivic Euler characteristic in terms of quadratic forms on coherent cohomology. So not an extra invariant in the Burnside ring.
Yeah, so that's also something I've wondered about, but I have nothing to say about it, unfortunately. Yeah. All that. Yeah, I don't know the answer to that. Yeah.
Is there any hope you could do this for Z mod P or other group?
Right, so that's the other natural question. And I think the answer is yes. The Z mod P case, when P is odd, should be a lot easier. And the reason is that what's making all of this complicated is the fact that you have isolated fixed points and the circles, the fixed circles, happening at the same time. Okay? For Z mod P, that's not going to happen. You can only have the isolated fixed points. Okay? So I don't think it's been worked out, but there's at least a starting place, and I sort of expect that part of the story to go easier. But for Z mod 4 and Z mod 8, right, those are going to be very interesting. They're just going to be even more complicated than what's here. Again, there's another thesis problem for somebody.
So I think we should defer further discussion till later, and thank you again.